Welcome to the Deep Dive, your shortcut to understanding the complex world around us, where we unpack the most critical insights from the sources you need to know. Today we're plunging into a topic that feels, well, more urgent with every passing season. How our buildings, our homes, our workplaces are kind of locked in this silent struggle with our increasingly strained energy grids. We've all seen the headlines, right? The accelerating climate crisis, escalating energy demands, and the tangible impact these global challenges are having on the very infrastructure that powers our lives. It's creating real stress on our electrical systems, threatening stability and, reliability. And at the heart of this escalating challenge for buildings is a concept called peak thermal loads. Now, this might sound a bit technical, but think of it simply. It's those moments when a building demands the absolute maximum amount of energy for heating or cooling, pushing the grid to its absolute limit. Picture a scorching summer afternoon when every single air conditioner across the city kicks into high gear. Or maybe a freezing winter night when furnaces are just running nonstop. These aren't just minor inconveniences. They create immense, sometimes, crippling stress on our power systems. And our mission today is to understand not just what these critical moments are, but more importantly, how intelligent building design can drastically reduce them. Our lens for this deep dive is a truly pivotal and, frankly, incredibly timely new development from the forefront of green building. It's the Energy and Atmosphere Credit EAc Reduced Peak Thermal Loads from LEED BD+C V5. New construction. EAc2, as you likely know, is pretty much the global benchmark for green building certification, setting the standards for what makes a building truly sustainable. The fact that they are now specifically recognizing and incentivizing this critical design approach tells us just how profoundly important it is for our energy future. So consider this your comprehensive guide to understanding how smart building design can slash energy demand, supercharge operational resilience, and secure vital points in green building certification. You're about to gain some surprising insights into the practical, groundbreaking strategies that are quite literally shaping the future of sustainable architecture and, empowering our communities. Okay, let's unpack this. How building design can be a powerful, often overlooked tool in securing our energy future. And hey, if you want to hear more deep dives into the exciting developments happening in this world, make sure to subscribe to our deep dive now. So let's kick things off with the fundamental why. Why this intense focus on something as specific as peak thermal loads? Building on what we just said, these are those specific instances when a building's internal temperature management, heating, or cooling requires the maximum draw of energy from the electrical grid. Yeah, imagine the entire city's electrical demand hitting rush hour traffic. But instead of cars, it's all the heating and cooling systems simultaneously flooring it. That's basically a peak thermal load for the power grid. And when do these peaks typically happen? In many regions, it's the hottest part of a summer day, often late afternoon, maybe between, say, 3 p.m. and 6 p.m. That's when the sun is just relentlessly beating down and everyone is cranking up their air conditioning to fight the heat that's built up all day. Or conversely, it could be the coldest part of a winter night, perhaps just before dawn, when temperatures plummet and heating systems are working overtime to maintain warmth against that biting cold. During these intense synchronized periods, the demand for electricity doesn't just climb, it skyrockets, puts immense pressure on the grid. And the consequences? Well, they can range from brownouts, where voltage drops and your lights might dim.
Right, that flickering effect.
Exactly. To full-blown blackouts, plunging entire neighborhoods into darkness. To try and stave off these failures, utilities often have no choice but to fire up what are known as peaker plants.
Ah, yes, peaker plants.
These are power plants designed specifically to kick in only during these moments of extreme demand. The stark reality is peaker plants are frequently older, less efficient, and, overwhelmingly run on fossil fuels.
Which makes them far more expensive to operate and significantly less sustainable. They're really a carbon-intensive stopgap.
Absolutely. A necessary one sometimes, but definitely not the long-term solution for a stable, clean energy future.
And what's truly revolutionary here, I think, is that a light isn't just asking for less energy consumption in a general sense. It's surgically targeting when that energy is consumed. It's really about how foundational design choices can create a more robust, more intelligent building. One that doesn't just sit there consuming power, but actively contributes to grid stability. When we connect this to the bigger picture, the core intent of LED LEED2 is, it's profoundly multifaceted. First, it's about a direct measurable reduction in peak demand on grid resources. Lowering that electrical rush hour consumption directly helps stabilize the grid. And that critically reduces the need for those expensive carbon-intensive peaker plants we just talked about.
Right.
This isn't some abstract architectural goal. It has a direct, tangible link to community energy security. It helps ensure power remains reliable for essential services like hospitals, emergency responders, and of course our homes, precisely when it's needed most. Second, and in my view, equally critical in our era of climate uncertainty, is the aim to dramatically improve overall building resilience.
Resilience. Okay, what does that mean in this context exactly?
Well, when we talk about resilience here, we're not just talking about energy efficiency, though that's related. We're talking about a building's inherent ability to maintain comfortable and safe conditions for its occupants and to keep critical operations running, even during power outages or extreme weather events.
Which, let's be honest, are becoming more frequent, aren't they?
Exactly. More frequent and more intense due to climate change. So, a building meticulously designed to reduce its peak thermal loads is inherently more resilient because it can naturally moderate its internal temperature for significantly longer periods without relying solely on external power.
So, like, during a heat wave, if the power goes out, the building stays cooler longer.
Precisely. Potentially for hours longer, which could literally save lives. Or, during a brutal winter cold snap, it retains heat far more effectively, maintaining warmth even if the furnace stops running. It's about self-sufficiency and, fundamentally, occupant safety. And third, this credit represents a really significant philosophical shift, I think. It strongly encourages energy-efficient envelope design and passive strategies first.
Before worrying about the fancy HVAC systems.
Exactly. This is a crucial distinction from some previous approaches that might have just focused on efficient mechanical systems. LEED is essentially pushing designers to think fundamentally about how the building itself interacts with its environment.
The envelope being the building's skin, basically. Walls, roof, windows.
That's right. It's literal skin, walls, roof, floors, and windows. And passive strategies mean leveraging natural forces. Considering a building's orientation to the sun, how much natural light it lets in, and importantly, how much heat it blocks, how it shades itself, or how its materials naturally absorb and release heat.
So making the building part of the solution.
You got it. Allowing it to moderate temperature without constantly demanding energy from active mechanical systems. It's a foundational shift towards designing buildings that are inherently smart and efficient from the get-go, rather than just, heavily conditioned boxes.
It's fascinating. It's like this credit is asking buildings to become better global citizens, isn't it? Okay, so we understand the why, the critical need to flatten these energy spikes for the grid and for our own resilience. Now let's peel back the layers and get into the how. What exactly does ENEED require to earn points under this crucial EAc2 credit?
Well, first off, there's a non-negotiable foundational compliance requirement.
Yeah.
Your project must meet ASHI 90.1 envelope compliance standards.
Yes, HAG 90.1, the big one.
Yeah, it's the widely recognized standard for energy efficiency in commercial and institutional buildings. It sets the fundamental baseline for how efficient a building's envelope should be. For those of you who really get into the technical standards, you'll know there are typically two main ways to show this compliance. There's a prescriptive path, which is like a checklist, basically.
Right.
Specified R values, U factors, etc.
Right. Or there's a building envelope trade-off path. This allows for some flexibility, right? If one part performs really well, it can maybe compensate for another part that's slightly less efficient.
As long as the overall envelope performance meets the standard, yes.
But what's absolutely critical here is that the version of HHRA 90.1 you use for this credit, EAc2, needs to precisely match the one you selected for another foundational prerequisite credit, EAP2. Minimum energy efficiency.
That's key for consistency.
Exactly. It's not just bureaucratic detail, it's vital. It ensures consistency across all your energy calculations and prevents any loopholes that could undermine genuine energy performance.
This immediately brings up an important question, doesn't it? Why the laser focus on the building envelope is very shell? Why is it so non-negotiable in this credit?
Yeah, why the first line of defense?
Well, it's because if that fundamental barrier isn't optimized, you are constantly fighting an uphill battle with your active mechanical systems. Your HVAC is always playing catch-up. And this brings us to a truly crucial rule embedded within this credit, the no trade-off rule.
Oh, yeah, the no trade-off rule. What's that?
The source explicitly states, and I'm quoting here loosely, Envelope efficiency cannot be traded off against other building systems like HVAC or lighting to meet these requirements.
So you can't just say, oh, my walls aren't great, but look at my super efficient AC.
Exactly not. You absolutely cannot skimp on your wall insulation just because you're planning to install a top-of-the-line air conditioning unit or use fancy LED lighting. The envelope, the physical skin, walls, roof, floors, windows must independently comply with those stringent ASHRE requirements. And this rule is, frankly, immensely significant because it fundamentally prevents projects from cutting corners on the most critical component of long-term energy efficiency. Think of it this way. If your walls, roof, and windows are leaky or poorly insulated, you're constantly bleeding energy, battling unwanted heat gain or loss no matter how intelligent or efficient your HVAC system claims to be.
Right, it's like trying to heat a house with the windows wide open.
Precisely. The core intent here is to ensure the building is inherently efficient from the ground up, that its foundational design is robust. Build that solid, high-performance thermal barrier first, then optimize everything else. This passive first, active second philosophy is what truly leads to resilient, lower energy buildings in the long run. It's a paradigm shift for many in the design and construction world.
Okay, that makes a lot of sense. Build the strong foundation first. And here's where it gets really interesting and actually quite adaptable, making it possible for almost any new construction project, right? Once you've met that foundational AHRE envelope compliance, that non-negotiable baseline, your project can earn up to 5 points under EAc2 by strategically combining any of the 4 available options.
5 points is quite significant in the ELEED system.
It is, and this offers incredible flexibility. It allows teams to tailor the approach to maximize the reduction of peak thermal loads for their unique context. Imagine a designer in a hot, arid climate like Phoenix. They might prioritize advanced shading strategies.
Whereas one in, say, Minnesota would likely focus much more on superior insulation and meticulous airtightness.
Exactly. The beauty of this point system is that it's not a rigid one-size-fits-all checklist. It's more like a menu of incredible powerful tools.
Tools that can be combined strategically to achieve optimal performance for a specific building, climate, and, importantly, occupant needs.
Okay, so let's dive deep into these 4 powerful compliance options. Let's understand not just what they are, but their maybe surprising impact. The first is option 1, enhanced envelope performance. This is really about taking that foundational envelope compliance we just discussed and kicking it up several notches. It's about making the building's skin an incredibly efficient, high-performance barrier. Think of it like designing, I don't know, a military-grade, super insulated jacket for the entire structure.
Or a really, really good thermos.
Yes. A super insulated thermos. The better its seal and insulation, the less energy you'll need to keep the inside exactly at the right temperature, regardless of the extremes outside. So what does this enhanced envelope performance truly entail, beyond just adding a bit more insulation? First, it means increased insulation levels that go well beyond the minimum code requirements in walls, roofs, floors.
Higher R values, essentially.
Right. More insulation means a superior thermal barrier, drastically reducing how much heat can penetrate your building in the summer or escape from it in the winter. This fundamentally makes your building far less susceptible to external temperature swings, allowing it to sort of coast through peak temperature periods with minimal energy input.
And often, the energy saved by going above code on insulation can actually outperform savings from more complex mechanical upgrades in certain climates. It's foundational.
Next, within this option, we're talking about high-performance glazing systems, windows, and doors.
Which are much more sophisticated than just standard double-pane windows these days.
Oh, absolutely. We're looking at features like microscopic, transparent low emissivity, or low coatings on the glass.
Those act like tiny heat mirrors, right, reflecting infrared heat.
Exactly. Keeping heat out in summer and during winter. You'll also find inert gas fills like argon or krypton between the panes.
Denser than air, so they slow down heat transfer. Better insulation.
Correct. And then there are selective transmission properties. The glass can be engineered to control exactly how much solar heat gain it allows while still letting in plenty of natural visible light.
So you get the light without the overheating.
Precisely. All of these features directly reduce unwanted solar heat, blasting in on a hot summer day, and critically prevent precious internal heat from escaping during winter. They essentially tune your windows to the climate. Then there's reduced thermal bridging. This is a sneaky one. And often overlooked, silent energy leak.
A hidden inefficiency that can really undermine even well-insulated buildings.
Totally. Thermal bridges are pathways in the building assembly like steel studs running directly through an insulated wall or concrete slabs extending from inside to out that allow heat to just bypass the insulation.
Like a highway for heat.
Yeah, exactly. Imagine that super insulated thermos we mentioned, but with a small uninsulated metal spoon stuck through the side. Even if the rest is perfect, that spoon is a thermal bridge.
Negating much of the insulation effort.
Right. So strategies to mitigate this include continuous insulation, which wraps the outside of the structure like a blanket, or structural thermal breaks, which physically separate conducting elements.
Addressing thermal bridging can yield surprisingly significant energy savings. It's often where a lot of heat loss or gain occurs without people realizing it.
And finally, within this option 1, we have improved air tightness, meticulously sealing the building envelope.
Preventing those uncontrolled air leaks, drafts.
Exactly. Stopping unwanted outside air from sneaking in and conditioned air from escaping out. Air tightness dramatically prevents unwanted heat transfer, both infiltration, like cold air leaking in during winter, and exfiltration, warm air leaking out.
But it's not just about energy, is it? Air tightness impacts other things, too.
Great point. It also dramatically enhances indoor air quality. By reducing the infiltration of pollutants, allergens, dust, unwanted moisture from outside, it creates a far healthier and more comfortable internal environment. You control the ventilation properly.
And if we truly connect this back to the bigger picture, a highly performing envelope isn't just a nice-to-have feature. It's the fundamental, foundational step towards a genuinely sustainable building. It's passive by nature. Once it's built right, it consistently reduces energy demand without any ongoing active management needed.
Set it and forget it almost.
In a way, yes, which leads to significant long-term operational cost savings and provides consistent occupant comfort. This proactive approach ensures your building is inherently robust against external temperatures. It's a durable, foundational investment that pays dividends continuously. It's one of the most powerful strategies for reducing peak thermal loads and enhancing overall resilience. It's about building that fortress against energy waste from the start.
Okay, so if we've super insulated the building skin with option 1, what else can we leverage from nature itself to keep temperature stable? That brings us neatly to option 2, passive thermal storage and shading. This is where intelligent design truly integrates with natural forces.
Designing with the climate, not against it. Exactly. Designing with the sun, the wind, the local climate, rather than just building a standard box and then trying to mechanically force its internal environment into submission with brute energy. This option strategically leverages natural elements and the building's inherent mass to gracefully moderate temperature swings and significantly reduce the need for mechanical heating or cooling during those crucial peak times. One key strategy here is thermal mass integration.
Okay, thermal mass. Like heavy materials.
Precisely. Imagine a massive, dense material like a concrete wall, a thick brick floor, or even heavy timber beams. These materials have the capacity to absorb and store heat, much like a sponge absorbs water. During the day, they can soak up excess heat from sunlight or internal activities.
And then release it later.
Yes. As the outdoor temperature drops in the evening, that stored heat is slowly, gently released back into the space, helping to keep the building warm passively. Conversely, in a hot climate, these materials can be night flushed.
Meaning you cool them down overnight?
Exactly. You use cooler night air, maybe through ventilation, to cool the mass down. Then, during the day, that cool mass absorbs heat from the building's interior, delaying or even completely eliminating the need for air conditioning.
Smoothing out the temperature curve.
Perfectly put. It smooths out daily temperature fluctuations, making the indoor environment far more stable and comfortable, like a thermal flywheel for your building. And we're seeing more use of engineered wood, mass timber for this. It offers thermal mass properties along with being a potentially more sustainable material choice. Next, within option 2 are strategic shading elements. And this is far more sophisticated than just interior blinds or curtains.
We're talking external features.
Yes, external architectural features. Carefully designed louvers, deep overhangs, fins, screens, even strategically placed vegetation like mature trees or integrated green walls. These elements are meticulously designed to block unwanted solar radiation, especially during those peak sun hours when the sun's intensity is at its most punishing.
And the key is blocking heat, not just light.
Absolutely. A well-designed overhang on a south-facing window, for instance, might let in the low-angle winter sun for passive heating, but effectively block the high-angle summer sun, preventing overheating.
Smart design.
Very smart. Green walls, too, beyond looking great, can provide evaporative cooling and add layers of shading, creating a cooler microclimate right against the building's surface. And finally, a highly impactful strategy, perhaps the most fundamental within passive design, is building orientation optimized.
Where you actually place the building on the site and which way it faces.
Precisely. Thoughtfully positioning the entire building in relation to the sun's path throughout the day and year, and also considering prevailing winds. For example, in colder climates, you might maximize glass on the southern facade to capture passive solar gains in winter. Sunlight penetrates and naturally warms the interior.
Free heat.
Essentially, yes. Conversely, western facades, often hit by harsh afternoon sun, might be designed with minimal glazing or very robust external shading to minimize heat gain during the hottest parts of summer days. So the building itself naturally regulates its temperature through its form and positioning.
Exactly. Making it inherently responsive to its environment rather than solely relying on energy-guzzling mechanical systems to fight against nature all the time.
So let's bring this back to the person inside. What does all this elegant passive design mean for you if you're an occupant? Well, from an occupant's perspective, the most noticeable benefit, and maybe one that surprises people, is just a profound sense of comfort. It translates directly to more stable temperatures, fewer uncomfortable drafts, fewer sudden hot or cold spots near windows, a more natural, consistent feel without constantly fiddling with the thermostat.
Which most people really appreciate. Absolutely. Imagine a space that feels consistently comfortable all day long, where the temperature doesn't swing wildly and the air maybe feels fresher, less processed by constant mechanical conditioning. That's the inherent beauty and sort of quiet luxury of passive design. It creates a more intrinsically comfortable, healthier, and genuinely pleasant indoor environment by working with nature. It's a noticeable upgrade to daily life. That's a powerful point about comfort. Okay, now let's shift gears a bit and explore option 3, active thermal energy storage. This is where buildings start to get really clever, almost like they're playing the energy market, making their own internal storage battery, but specifically for temperature control.
Shifting energy use in time.
Exactly. Instead of relying solely on real-time grid power for heating or cooling, this option involved deploying sophisticated technologies to store thermal energy either hot or cold at off-peak times, and then strategically releasing it during peak demand. It's effectively shifting energy consumption.
Allowing a building to buy low, use high in energy terms.
Yeah, buy power when it's cheaper and less strenuous on the grid, and then use that stored energy later when it's most needed, reducing that critical peak demand. One of the most common applications of this is ice or chilled water storage systems. How do these work? Well, the mechanics are pretty elegant. At night, when electricity demand is typically lowest and electricity prices are often cheaper.
Off-peak rates.
Right. Chillers can be run to create large amounts of ice or simply chill water to a very low temperature. This cold energy is then stored in massive, well-insulated tanks. Then during the day, especially during those peak hot hours when AC demand is highest, the building doesn't have to fire up its big energy-hungry chillers and pull massive power from the grid.
It just uses the stored cold.
Exactly. It simply circulates water through the stored ice or chilled water to cool the building. This dramatically cuts the building's peak electricity consumption.
Which eases strain on the grid and can deliver substantial savings on utility costs, especially with demand charges.
Definitely. Those demand charges for peak usage can be killers on a commercial bill. So this decouples when you make the cold from when you use the cold. Similarly, we have hot water storage tanks. The principle is identical, just for heating.
Storing heat instead of cold.
Right. Hot water can be heated during off-peak hours using electricity or maybe other energy sources like solar thermal, and then stored in insulated tanks for use when demand is high. This could be for domestic hot water sinks, showers, or for space heating during those cold morning peaks.
Again, the core idea is consistent. Produce or store energy when it's cheap and abundant, store it efficiently, and then deploy it when it's most beneficial, economically, and for grid stability.
And then there's this really fascinating, almost futuristic-sounding technology. Phase change materials, or PCMs.
Oh, PCMs. These are very interesting.
They really are. They're not just simple liquids or solids. They are substances engineered to absorb and release surprisingly large amounts of latent heat as they melt and freeze at very specific design temperatures.
Latent heat being the energy absorbed or released during a phase change without the temperature changing.
Exactly. Think of it like a highly efficient, endlessly reusable ice pack, but one that's integrated right into your building materials. When a PCM melts, it absorbs heat from its surroundings. When it solidifies or freezes, it releases that stored heat.
And these can be integrated into things like drywall.
Yeah, integrated directly into building materials like drywall, ceiling tiles, or even used within HVAC systems. For example, a PCM could be designed to melt at, say, 75 degrees Fahrenheit, a comfortable room temperature. As the room warms up past that point, the PCM absorbs heat and melts, essentially buffering the temperature increase, keeping the room cooler without active cooling kicking in as hard.
And then releasing heat as it cools down below 75.
Exactly. As the room cools, the PCM solidifies and releases that stored heat, preventing it from getting too cold. It allows buildings to store and release thermal energy almost passively.
Reducing peak loads without needing massive water tanks. More compact, often invisible.
Right. A highly efficient solution for thermal management embedded right in the building fabric.
What's truly fascinating here, and what really represents that paradigm shift I mentioned, is the inherent flexibility these active storage systems offer. They profoundly decouple energy consumption from energy use. That's the key takeaway. This allows a building to respond dynamically to real-time grid conditions, to potentially save significant costs by buying power when it's cheapest and most readily available.
Becoming an active player in the energy market.
Essentially, yes, an active prosumer of energy rather than just a passive consumer. This active management is a significant leap beyond traditional building operation. It transforms buildings from mere energy sinks into strategic energy assets, into, as you said, living batteries for the grid.
Providing a buffer.
Exactly. A critical buffer allowing buildings to coast through peak periods by intelligently drawing on their own stored energy rather than adding to the grid stress. And this capability becomes even more invaluable as we integrate more intermittent renewables like solar and wind.
Ah, good point. Store the solar energy thermally when it's sunny.
Precisely. Store thermal energy allows buildings to intelligently use that renewable power when it's plentiful, then deploy it strategically when the sun isn't shining or the wind isn't blowing. It contributes to a far more stable and efficient overall energy system. It really is a potential game changer for grid modernization. That's an excellent point about buildings becoming active grid participants, which leads us perfectly into option 4. Load shifting and demand response. This option truly represents the cutting edge of building intelligence. It's about transforming buildings into active partners in grid stability, not just passive consumers.
Making buildings smart in a way that actually helps everyone.
Exactly. Creating smart buildings that can think, adapt, and respond in real time. This involves actively managing energy consumption, often in dynamic response to signals directly from the electrical grid, specifically to reduce demand during those critical peak periods. A core component here is automated HVAC control systems. We're talking intelligent building management systems, or BMS.
The brain of the building's operation.
Pretty much. These systems can automatically and strategically adjust heating, ventilation, and air conditioning operations based on various inputs, occupancy, weather forecasts, grid signals. For example, before a predicted peak period, the BMS might pre-cool building, subtly lowering the temperature maybe a degree or two below the normal set point.
Using cheaper off-peak power to do it.
Right. Then, during the actual peak, the HVAC system can intelligently scale back or even temporarily shut off for short periods, relying on the building's inherent thermal mass and that pre-cooling effect to maintain comfort.
Or just let the temperature drift slightly within the comfort band.
Exactly. Maybe allow it to drift up by 1 or 2 degrees in summer or down in winter. These small adjustments, when implemented across many buildings simultaneously, can yield surprisingly significant aggregate energy savings for the grid. Even more advanced are demand response-capable building controls. This is where buildings truly enter into a dynamic dialogue with the utility grid.
They actually talk to each other.
In a sense, yes, through data signals. When the grid is stressed, maybe due to an unexpected power plant outage, an extreme weather event, or just unusually high demand, the utility can send out a demand response signal or price signal to participating buildings.
Like an SOS from the grid.
Sort of. And in response, the building's controls automatically take action to reduce non-essential loads. This might involve dimming lights slightly in common areas, adjusting temperatures within that predetermined comfort band, or, if the building has storage, switching to stored energy from a thermal storage system or even an on-site electrical battery.
So the building actively helps the grid avoid problems.
Precisely. This active participation from buildings is a crucial tool for grid operators. It helps them avoid blackouts and maintain grid stability for the entire community. It's about distributed intelligence, turning buildings into a dynamic, flexible resource for the whole energy ecosystem. And finally, this option profoundly integrates energy storage and management strategies. We mentioned thermal storage under option 3, but here we can also explicitly include electro batteries, all managed by sophisticated smart controls.
So, like Tesla Powerwalls, but potentially on a much larger scale for commercial buildings.
Exactly. Imagine a large commercial building with a substantial battery bank. During off-peak hours, when electricity is cheap and maybe renewables are abundant, the battery charges up. Then, during peak demand periods when grid power is expensive or strained, the building can draw power from its own battery instead of the grid.
Reducing its peak draw.
Or, in some cutting-edge scenarios, if the grid is really stressed and the utility signals for it, the building could even send power back to the grid from its battery, becoming a temporary net exporter of energy.
Wow, so the building becomes a mini power plant almost.
In a way, yes. When you combine battery storage with thermal storage and intelligent controls, the building can make highly strategic, economic, and grid-supportive decisions in real time. It can decide, should I pre-cool using cheap renewable electricity now, or should I charge my battery to offset a different electrical load during peak times later? This level of integration truly transforms buildings into dynamic energy hubs that can intelligently balance their own demands with the evolving needs of the wider grid. They become indispensable parts of the smart energy future.
So let's bring this back to the person on the street or in the office. What does this all mean for you, the individual interacting with these buildings, or maybe living or working in one? Well, it means your building isn't just a structure, it's becoming a sophisticated, responsible citizen of the energy grid. It's actively and often invisibly helping to prevent blackouts, reduce the need for those dirty, inefficient peaker plants, and ensure reliable power for everyone in the community.
You might not even notice the changes.
Probably not. You might not even notice these subtle adjustments in temperature or lighting levels, but the cumulative impact on grid stability and overall community energy resilience is profound. It's part of a silent, sophisticated system working in the background to keep our modern lives powered reliably and sustainably. It really does shift your perspective on the unseen work happening behind the walls, doesn't it? Okay, now let's just quickly circle back to what we call the essential foundation. Those envelope compliance details and best practices. We touched on it earlier, but it truly cannot be stressed enough. The specific version of A to Z Array 90.1 used for envelope compliance, whether you use the prescriptive path or the trade-off path, must be consistent with the version chosen for EAc2, the minimum energy efficiency prerequisite.
Consistency is paramount.
It really is. This isn't just some bureaucratic detail or a technicality only engineers need to worry about. It's an absolutely critical requirement. It ensures a holistic, transparent, and standardized approach to energy performance across the entire LEED certification process. It means your building's energy performance is being evaluated against a consistent, reliable benchmark.
Preventing any fudging of the numbers or loopholes.
Exactly. It prevents miscalculations or gaming the system that could undermine real sustainability. This consistent baseline guarantees that the whole deep dive into efficiency starts from a verified, rigorous foundation.
And this brings us right back to what we highlighted as the no compromise rule, which is, I think, a powerful philosophical statement from LEED. To reiterate, the source definitively states, envelope performance cannot be compromised or traded off against other energy systems. The envelope must independently comply.
The high-tech winter coat analogy again.
Exactly. The underlying philosophy here is absolutely fundamental. A truly energy-efficient and resilient building must begin, with a high-performing enclosure. Think of putting on that perfectly sealed, well-insulated, high-tech winter coat before you even consider how powerful your internal heating system needs to be. If that coat is leaky, thin, or poorly fitted, no matter how powerful your internal heater is, you'll still be cold, uncomfortable, and wasting an enormous amount of energy constantly trying to compensate.
Makes perfect sense.
The building's enclosure, its walls, roof, foundation, windows, is the primary interface with the outside world. If that foundation isn't optimized, you're constantly fighting an uphill battle against heat gain or heat loss. It makes all other energy-saving strategies far less effective and potentially means you have to oversize your mechanical systems, adding cost and complexity.
So design intrinsic efficiency first.
Build that thermal fortress before you add the cannons, so to speak. This is where real, enduring energy performance is born.
That's a powerful way to put it. It highlights how much that upfront investment in smart design really pays off down the line. So understanding this critical foundation, How do we ensure all this happens successfully in practice? What are the actual best practices for designing buildings that truly embody these principles and effectively reduce peak thermal loads?
Well, it starts fundamentally with engaging architects and building envelope specialists early, really early.
Not bringing them in at the last minute.
Absolutely not. This is crucial. These experts need to be part of the conversation from the very initial concept stages of a project, not as an afterthought once the basic design is already locked in. This early integration maximizes opportunities for passive design integration. It allows a building's form, its orientation, its material choices to naturally contribute to optimal thermal performance,
Instead of trying to tack things on later.
which is always more expensive and usually less effective. It's about designing with efficiency from day one.
Exactly. Then, following from that, it's about selecting high-performance, low U-value windows and robust insulation systems. This connects directly back to option 1, our enhanced envelope discussion. U-value, just to remind folks, measures how well something conducts heat. Lower is better, meaning better insulation.
Right. Less heat transfer.
These material choices are fundamental to creating that superior thermal barrier we keep talking about, drastically reducing heat transfer in and out.
Investing in these elements upfront means you're locking in energy savings for the entire lifetime of the building. It's a long-term value proposition. And this naturally leads to the next best practice, incorporating shading and passive thermal strategies from initial concept stages. This links directly to option 2. Passive strategies like those strategic overhangs, external louvers, or integrating thermal mass work best, and are certainly most cost-effective when they are baked into the design from the very first sketch.
Rather than trying to retrofit later.
Exactly. Trying to add significant external shading or substantial internal thermal mass later is often difficult, can look awkward, is prohibitively expensive, and almost always less effective than if it was planned from the start. It's about aligning the building with its climate intelligently, making the climate work for the building.
Okay, and a really powerful, almost indispensable tool in this entire process is to model the building early, to predict peak loads and optimize designs accordingly.
Energy modeling, absolutely critical.
Yeah, leveraging advanced energy modeling and simulation software.
Mhm.
It allows design teams to create a sophisticated digital twin of the building, and then they can test almost infinite array of different scenarios.
Mhm.
What if we use this type of glass here? What if we orient the building 5 degrees differently? What if we add continuous insulation versus just cavity insulation?
You can iterate and compare outcomes before spending a dime on construction materials.
Exactly. This incredibly powerful capability lets project teams identify potential peak load issues and refine their strategies long before construction even begins, saves significant time, avoids costly rework, ensures optimal performance right out of the gate. It's designing with data-driven precision.
And finally, a truly holistic approach means leveraging thermal mass and active energy storage strategies to balance thermal demands effectively. In many real-world applications, the optimal solution isn't just one option, but often a smart combination of strategies. Intelligently drawing from both option 2, passive thermal mass, the inherent capability of materials, and option 3, active thermal storage, the mechanical ability to store energy.
Using both passive and active approaches together.
Right. This blended approach often creates a far more balanced, flexible, and resilient building system, one that can handle diverse external conditions more gracefully, respond intelligently to dynamic energy prices or grid signals, and better withstand unexpected stresses like power outages. It's about building a versatile, adaptive energy performer.
It certainly sounds like a massive amount of foresight. Deep interdisciplinary collaboration between architects, engineers, envelope consultants, and sophisticated modeling are absolutely key here. It's really about designing with the end in mind, isn't it?
Yeah.
Recognizing that every single decision, from the initial site planning right down to the granular selection of individual materials, profoundly impacts the building's energy footprint and its ability to gracefully manage those critical peak loads throughout its entire lifespan.
Precisely. And this raises an important question for all of us involved in buildings, and even for those just using them. How do these best practices ensure not just compliance with a LEED credit for points, but truly optimize performance? And critically, how do they deliver a higher quality building for every single occupant? It's about creating buildings that are genuinely future-proof, built not just for today's energy prices or codes, but for tomorrow's climate realities and the evolving demands of our power grids. They really are investments in long-term resilience, comfort, and value.
So we've gone deep into the mechanics, the options, the best practices for designing buildings that tackle these peak thermal loads. But let's just take a step back for a moment and really look at the profound bigger picture. Why does reducing peak thermal loads genuinely matter? Not just for a LEED point, but for all of us, for our
Yep.
communities, for our planet. Well, first, and perhaps the most immediately tangible benefit, especially for building owners and managers, it translates directly into lower operational energy costs and utility bills.
The bottom line impact.
Absolutely. When a building is meticulously designed to flatten its energy consumption peaks, it avoids those often punitive demand charges that utilities impose during high-stress periods. This directly translates to significant measurable financial savings month after month, year after year, over the entire lifetime of the building. It's a compelling win for the balance sheet. It makes these sustainable practices financially intelligent decisions.
And that financial benefit is often directly linked to a far more critical outcome, especially these days: enhanced resilience. As we've discussed, this isn't just about the building being more energy efficient in general. It's about its profound ability to better withstand adverse, sometimes even life-threatening conditions.
Because it holds its temperature better naturally.
Exactly. Because these buildings are naturally better at maintaining a stable internal temperature, they become far more robust during power outages or extreme weather events. Imagine a hospital wing or an apartment building housing vulnerable people that can stay comfortably cool for hours, maybe even days, without power during a severe heat wave, or retain its warmth during a brutal winter storm when the grid goes down.
That's huge for safety and well-being.
It's absolutely critical. It directly translates to increased safety, security, and comfort for everyone inside. This isn't abstract efficiency, it's real-world preparedness for a changing climate and an increasingly unpredictable grid. It's a crucial measure of true societal preparedness.
And then beyond the individual building, there's that massive, often unseen community benefit. Reduce stress on local power grids. When buildings collectively start to significantly reduce their peak demands, the entire electrical grid breathes easier.
Less strain during those critical hours.
Right. This means fewer brownouts, significantly fewer blackouts, and overall, more stable and reliable energy resources for the entire community. Every single building that effectively manages its peak load is making a real, measurable contribution to broader energy security and the well-being of its neighbors, its city, its region.
It's a powerful collective action.
It really is. It makes a tangible difference in ensuring that our essential services and our everyday lives remain reliably powered, especially when we need it most.
And finally, let's not forget a profound benefit that directly impacts our daily experience and our well-being inside these buildings: improved occupant comfort and indoor environmental quality. When a building is intelligently designed to passively moderate temperature, ensure good ventilation, and meticulously reduce air leakage, you get far more consistent indoor temperatures.
Fewer drafts, fewer hot-cold spots.
Exactly. And crucially, you often get significantly better air quality because that uncontrolled infiltration of outside pollutants, allergens, dust, and moisture is minimized. You're breathing cleaner air. This creates a more pleasant, healthier, and ultimately more productive environment for people living, working, learning, or healing in these spaces.
It's about creating spaces where people don't just feel okay, but where they can truly thrive.
It elevates the human experience within the built environment, which should always be a primary goal of good design.
So what does this all mean for you listening right now? It means the buildings around you, the ones you inhabit every day, maybe even your own home, are becoming dramatically smarter. They're becoming inherently more robust, more resilient, and profoundly more considerate of the wider energy landscape we all share. They're not just passive structures anymore. They're becoming active, intelligent participants in our collective energy future.
Quietly working behind the scenes.
Exactly. Quietly working behind the scenes to make our communities more sustainable, more resilient, and ultimately more prepared for the escalating environmental and energy challenges we face. It's an unseen revolution happening in plain sight in the very walls around us. We've taken a really deep dive today into LEED V5's EAc2 credit, reduced peak thermal loads. And what it really boils down to, I think, is that powerful, concise mantra from the source material itself. Design smart, shift wisely, build resilience.
Sums it up perfectly.
It really does. This credit and the groundbreaking strategies we've explored today reveal a clear, actionable roadmap for creating buildings that are not just energy efficient in a generic sense, but truly future-proof. They stand as testaments to intelligent design, quietly but powerfully contributing to a more stable grid and a more comfortable, sustainable world for everyone. So here's a final thought to leave you with. As you look around at the buildings in your life, maybe your office, your school, or even your own home, what single strategy for reducing peak thermal loads that we talked about today do you think could make the biggest, perhaps most surprising difference right now? How might this deep dive shift your perspective on all the unseen and genius work happening behind the walls to create a more resilient world for all of us? And remember, if you want to hear more deep dives into the exciting developments shaping our built environment and our energy future, make sure to subscribe to our deep dive now.